Hi, I'm Max Clark, and in IT, more is less. I'll give you 3 examples. Maybe I'll give you more examples, but I'm going to start with 3 examples. In the late 90s, early 2000s, the rage was Java application development. And we had application servers like BEA WebLogic that hit the market, and then incredible options from the Apache project with Tomcat, and then JBoss, and IBM had a platform. I mean, it was, if you were doing enterprise development and you were building enterprise platforms, odds are you were using Java to do it. And by the way, Java is still very much a thing today. It just doesn't get the same hype cycle as it had at that point. Part of what you had to do when you were tuning and doing performance profiling optimization on a Java application server was JVM heap tuning. Bear with me, but if you know Java and program with Java, you'll understand this reference. If you don't, I'm going to try to explain it to you in a way, which is if you think about having a bucket and you slowly pour water into the bucket, and when the bucket fills up, you then have to pour the bucket out. And this is basically what happens with Java and its heap. So heap is memory and it's an allocation. So when the application creates references to data, stores data, conducts operations, etc., it adds things to its memory, right? So just think of the visual in terms of putting water into a bucket. And the issue with Java and JVM and heap profiling and heap settings is there were a lot of knobs you could turn. Like, what was the actual methodology? What was the mechanism for, how it would reclaim heap, right? Was it dipping a ladle into the bucket and ladling out? Was it pouring the bucket out? Was it poking holes in it, right? Like, there's different algorithms that would actually approach this. And then you had other options in terms of tuning, how big the heap was. By the way, this is basically what most people just did, was set how big the heap was, but you could actually manipulate a little bit how the algorithm worked. You could select the algorithm, you could select which JVM you were running. The JVM would function a little bit differently. Like, were you running Suns? Were you running IBMs? Were you running, OpenJDK? Like, there was different things that you could do. And of course, then, by default, you get into a conversation with somebody and they'd say, hey, by the way, back then RAM was really expensive. Like, a gig of RAM was like, holy smokes, we got a lot of RAM. But you get into these conversations of like, oh, we've got a Sun E420 server and we've put 8 gig of RAM in it. Let's just give 6 gig of RAM to the heap, to Java, and like, it'll be so unbelievably fast. Like, it'll be incredible. And in this case, more is less. And every Java application environment that I've ever been involved with, when we actually started going through profiling and tuning, you find that by giving it less memory and giving the heap less space, that operation to clean itself out runs faster, which is what you more than likely actually care about, because there's conditions where the application server would just pause. It could do nothing until that operation completed. So by going from a bucket, like a trash can, to a bucket, to maybe, a pitcher, and I'm trying to use like visual references here. On the surface, you think about that, and you're like, oh no, the bucket's way better because we can put more stuff in it. But the pitcher empties so much faster that it actually gives you what you want, which in many cases is just a really fast application and a really fast experience for your users. And again, right, really specific to the application. If you had something and you needed to store, like for some reason that much, your application needed, 1.2 gig worth of heap, right? Like, you couldn't give it 500 mega heap. Like, it wouldn't work, right? But again, we're talking in general here. In general, more is less, right? So we need less, and then less becomes more. Another example that I still see to this day, which is wireless coverage inside of buildings. And you get into a conversation, and the conversation kind of goes like, hey, we have really bad wireless performance in this building. Let's just go buy more access points. Sounds great, right? Like, you've got 8 access points right now. I mean, you're going to buy 4 more, you're going to have 12. Like, why not just get 30 more? Why not have 38 access points? You could have an access point on top of everybody's head, just running the entire building. Same issue. More is less. If you haven't gone through and actually taken and done a study, a wireless distribution study in that building, you do not understand what is actually going on and why signal might be bad in certain areas. You might have interference. I had a client, and their designer had this really fancy interior plan, and there was large glass windows on offices. So, kind of your typical thing where you'd think like, a row of offices on the outside window with bullpens and shared space on the inside, and then like cool collaborative work areas where you could kind of go in and, like think like a conference room. And they put these really cool window coverings and designs and patterns and, art and stuff on these windows. And it was really cool. Only problem was whatever the freaking material was. I mean, I'm assuming it wasn't lead because that'd be a big no-no in the US, right? But whatever the material was absolutely nuked Wi-Fi signal. So, I mean, in a lot of cases, there was a Wi-Fi access point sitting, like 25 feet away from that conference room with a glass window. And you're like, why can I not have it? Is there no wireless signal in this room? And you're like, oh yeah, whatever is on that window, it's like, it's like a Faraday cage for Wi-Fi signal. That was a fun one. So, you really do want to invest the time and try to do a wireless study. If you can, it's worth it. You'll come through, they'll give you a map, they'll figure out different Wi-Fi placement, they'll find hot zones, they'll find cold zones, they'll tell you, where signal is not propagating. They'll find things that are interfering with signal, air conditioning, ducting, pump motors, beautiful art on your conference room windows, whatever it actually may be. And we'll help you figure out and actually tell you, how many APs do you need and where you want to go with it. Also a big difference between 5 gigahertz and 2.4 gigahertz and then of course with Wi-Fi, 6, starting to see devices support it, and then Wi-Fi 7, coming out in terms of AP. Like this changes the games again in terms of what frequencies and what spectrums you have to actually run. But let's just stick with 5 and 2.4. If you have an access point that supports the 5 gigahertz band, it also supports 2.4 gigahertz band. The 2.4 gigahertz band goes a lot farther than the 5 gigahertz band. And now you have to deal with handoffs. How does one AP hand off to another AP? And how does the device know to hand off? And maybe that device will go and switch from 5 gigahertz to 2.4 gigahertz. And you'll be walking through and you'll be under another access point, but your device is still talking to the AP down the hall. And you've switched from 5 gigahertz to 2.4 gigahertz, your performance is lousy, and you're looking up and there's an AP right above you, but like, why do you get bad service? And the answer again, more is less. Resist the temptation just to go out and buy 30 access points, because what you really need to understand is what the heck is going on with your access points in the first place and your signal. And do you need to go through and change the channels that you're on? Do you have interference from your neighbors or something else in your space? Do you need to go through and tune your power output and receive sensitivity on your APs? Do you have to go through and configure how they hand off to each other? And the answer, by the way, open book test, the answer to all those things is yes, yes, and yes. And if you haven't done that, you have to go do it. AP manufacturers, I'll tell you, they do this automatically. Some of them tell you that they have fancy AI that does this for you automatically. Whatever. Trust me. Yes, yes, yes. You have to do it. You have to do it. You have to do it. So more is less. What's another good one? More is less. Redundancy. Redundancy is a more is less thing for me as well. And if you've never configured spanning tree on a switch stack, I envy you. And if you have configured spanning tree on a switch stack, you understand why I'm laughing. We need redundancy. We can't have any single points of failure. Like, let's throw more network devices at the problem. We need to have, and this, by the way, the spiral's out of control really quickly. Okay. We need to have a switch. We're going to plug something into that switch. Oh, that switch is now a single point of failure. Let's get dual power supplies in that switch. Okay, great. Now it's got dual power supplies, but still a single switch. Let's get a second switch. Okay, great. We have 2 switches with 2 power supplies. Are our PDUs separate? Okay, good. They're separate. Are they running to different electrical distribution panels or switches? Yes. Okay, great. Do those have different batteries behind them? Yes. Okay, great. Do those run into different generators? This is like a tier 4 data center design. You probably don't have this in your office, but we can just keep talking through this. Okay, so now you have 2 switches. You have 2 switches. Now your server needs 2 NIC cards. Okay, it's plugging into 2 switches. How does the server decide which NIC it's sending traffic over? How does the network decide what interface serves back down to you? And by the way, here's a little aside pro tip. When you are doing bonding or teaming with your network interface cards, with your NICs on a server, if you have 2 25 gig NICs in a server, or 2 10 gig, let's just say 10. If you have 2 10 gig NICs in a server, yes, you can build an Ether channel, you can team them, you can bond them, whatever terminology you want to use, I don't care. And in theory, you now have 20 gig of capacity. And yes, you do, in theory. The caveat to that is your maximum stream for data. Like if you're doing a data transfer, unless you're breaking that data transfer up into multiple streams of transmit, it will saturate at the network interface, right? So you've got 20 gig worth of network, right? But you really only have 10 gig for data transfer. So if you were wondering why things aren't working in our network, it's probably just because of that. Anyways, so now you've teamed the 2 NICs. Which switch is it talking to, right? So what do you have to tell the server? You have to tell the switches which interface is coming down. How do you manage that? Okay, now you've got 2 switches that your server's plugged into. Then those 2 switches have to go plug into 2 and we can talk about leaf and spline. We can talk about, what your core distribution looks like. Let's just keep it really simple and just say you've got some sort of central distribution with some sort of like in-rack distribution. Or if you're in an office, you've got switches in an MDF on a floor, and those switches in the MDF then come down to some sort of central aggregation point or core distribution point, right? Well, now, of course, you have to have two switches in that core, right? And you need a firewall. But nope, you need two firewalls. So those two switches have to plug into two different firewalls, and those two different firewalls now need to have two switches on the outside of those firewalls, and those switches on the outside need to have redundant interconnections. Maybe you have routers, maybe you don't. Maybe your switches are your routers. And what you've created is you've got a really nice diagram now where, like, if you just draw the public side of your firewalls and your switches and your inside side, you've got a lot of lines on that diagram, right? Because your firewalls, more than likely, your default is your firewall is going to have 2, 4, 5 interfaces on it, right? So it's got one to each top switch, one to each bottom switch, and going into each other, right? So there's 5 interfaces. And this isn't like you just plug it in and it works, right? This is you have to plug it in, and now you have to go through and you have to start configuring each element of your network with how it actually sends traffic on a normal state, and then also on a failure state, what happens, and how do you define a failure state, what goes on with it. And then at some point, you finally add that one last magic piece of device, and you have no idea why, but you plug in a fish tank, and the entire thing just goes just stops working. And then, after spending hours trying to figure out why it isn't working and struggling, maybe you call somebody like me in a past life in, and we get to physically unplug every network cable, trace everything, plug everything back in together, and then rebuild this over a really excruciating long weekend where we don't sleep for 80 hours to get your network back up and running. So that way you can process orders and ship product out your warehouse. And by the way, this is a true story. And if you notice my attitude right now, I was supposed to be on vacation when that particularly story happened, and, didn't happen for me. But anyways, a lot of times in IT, more is less. So, before you throw stuff at the wall and hope it solves the problem, maybe just take a moment and think about it. Like, how often does a switch actually fail? Like how, I'm not talking about infant mortality rates. I'm not talking about you bought, 500 switches from, non-enterprise switches, but, 500 switches from your, server manufacturer of choice. And you're expecting, 10% of them just to not work when they unbox. But how often has your switch failed? And what happens if it does fail? And what is your recovery pattern of having two switches and trying to have them both online at the same time versus just having a switch in the box sitting next to it that you can take and plug into the rack and move all your cables? And also, pro tip on this one, print out the config and have the config taped to the device that you're going to replace. Now, you should have config management and you should be doing a bunch of other things, but in a pinch, if you've got that config printed at least to a state that you knew that device was working and you can type in all the commands sequentially, you can get back online, and it's usually really fast. Almost might be faster than trying to get the config management system talking to that device and pushing that config back down to it. I'm a really big fan of just having spares on site. Most applications, unless you really do have a true life and death or measurable financial impact that dictates that level of redundancy, don't poo-poo on having, single devices, a single firewall, and a single switch distribution with a single edge. Like, it's a really simple network. It's hard to break that. It's hard, for bad things to happen to you there. It's not as sexy. I get it. But, more is less. Anyways, I'm Max Clark. If you have questions, comment below. Yes, you should have redundancy, and people are going to yell at me for that. And if you want to just get into it, fine. I'll be there for you in the comments, go for it. But anyways, hope this helps. If you have any questions, need help, reach out. Happy to help.